Hi everyone, welcome back. My name is Prayush Kumar. I'm one of the co-organizers of this program. And it is my pleasure to welcome Dr. Nils Siemonsen from Princeton here today to deliver the first lecture of the second lecture series this week. Nils is a computational relativistic astrophysicist whose main focus of his research has always been compact objects in highly dynamical situations, highly dynamical spacetimes. He did his PhD from Prince Perimeter Institute before joining the Gravity Initiative at Princeton University. And this week he'll talk about ultralight boson clouds around black holes. So without further ado, please take it away.
Thank you for the kind introduction, and also thank you for the kind invitation. It's always great to be back in India. So these couple of slides are just meant to kind of introduce the topic at a very broad and intuitive level, and kind of outline the history of how these things developed over time. And kind of you can see it's kind of a summary or a table of content of what's to come in the next couple of days. Okay, so it's of course about black holes, and we'll get to the ultralight boson part, but let's first focus on black holes. So back in the 70s, a bunch of people, including some of the people named here, were considering rotating spacetimes in general and rotating black holes in particular. And what they noticed is that in particular situations, you can have the following occur. You can have a pulse of some wave coming in onto a rotating black hole, and then scattering off this black hole in a particular way, all of which we'll understand in the next couple of days. And then what will happen in certain circumstances is that the reflective amplitude is larger than the incoming amplitude. And that basically means that you get out more energy than you put in, and they call this superradiance, because you, in essence, extract rotational energy from the black hole through the Ergoregion of the black hole. Okay, so now imagine, okay, we have, let's say, I don't know, a scalar wave scattering off this black hole. And this scalar wave then, gets energy, extracts energy from this black hole, and then moves out to infinity. Now this is all great, but then, the pulse is gone and it will never interact with the black hole again. So how can we make this pulse interact with the black hole many, many times? And so the way to do this is to add a mass term to the scalar field, because through the mass, it's then gravitationally bound, or it can be gravitationally bound to the black hole, and then repeatedly interact with the black hole, and presumably extract more and more rotational energy over time. So then in the 80s, Dedwell noticed exactly that. He found that if you add a mass term to the scalar field, then it won't just scatter once, but instead there are states, bound states around the black hole that grow exponentially in time. And so they extract more and more energy from the black hole and kind of deposit it in a cloud that sort of oscillates around the rotating black hole. All of which we'll understand in detail in the next couple of days. And so for certain reasons, this is called the gravitational hydrogen atom, basically because at least a partial, a subset of the underlying equations are identical to the usual hydrogen atom in quantum mechanics. Okay, so what we have now is, okay, we have this kind of cloud that sits around the black hole that extracted a large amount of energy, and it turns out that this cloud is oscillating around the black hole. Okay, so now we have some time-dependent quadrupole. We have something that has a lot of mass that can oscillate, and so it will emit gravitational waves. And so this is a little movie of basically just showing you, wrong laptop, showing you, okay, there's the cloud at the center, and it kind of happily oscillates around the central black hole. And then in green, there are these gravitational waves being sent out to infinity. And as you can kind of spot already, these are basically monochromatic or continuous waves. They have a set frequency, and basically they evolve only very, very slowly in time. Okay. Okay, And then in the 2010s and early 2020s, then people started realizing, okay, we have this strange process through which some scalar, massive scalar fields can extract energy from a rotating black hole, but how is that astrophysically relevant in any sort of way? And so the key insight there is to notice that in particle physics, people have predicted particles to exist that have a mass. And so these particles then, are potentially scalar particles that potentially have a mass. And if this mass satisfies a certain condition, then it will trigger this process. And so the mass range that is relevant here, the boson masses, are basically between 10 to the minus 20 and 10 to the minus 12 electron volts. And it will become clear later on why this particular mass range and not another mass range. And so these authors basically came up with a way to motivate, from a particle physics point of view, that these particles should exist, or may exist, basically to solve certain problems, like, for instance, you've heard of the strong CP problem, where the axion, the so-called axion, solved this particular problem. The details aren't too important, but basically you can motivate through particle physics means the existence of these ultralight bosons. And so then potentially, if these were to exist, and we haven't observed them yet, maybe this superradiance process around a rotating black hole is a way to look for signatures of the presence of, first the superradiance clouds, but then also of the existence of the bosons. Okay, and ultimately, what we're kind of interested in with this whole superradiance game is to do something like this. So particle physicists love to look at these plots. Basically, what you're looking at is on the y-axis, you have the kinetic mixing, or some particular coupling between these new bosons and the standard model. Now, what the kinetic mixing is doesn't really matter. It could be a different kind of coupling. But basically, this is, the larger the number, the stronger the coupling to the standard model, and the more obvious we'll be able to tell if this particle existed or not through, some experiment we can perform. And so the weaker the coupling, so the smaller the number, the harder it becomes to detect these things, because they're weaker coupled to things that we have in our labs, like experiments, are all based on standard model matter. And so basically, all these colors indicate one experiment or one way of excluding this particular part of the parameter space with some measurements. And so basically, what you can see is that the general trend is that the stronger the coupling, the more colors there are, and so the more and stronger constraints we have on the existence of these particles. So basically, roughly speaking, everywhere there's a color here means that we are confident that this particle doesn't exist, right? But then conversely, on the bottom side of the plot, there's just white, because basically we can't make a measurement there that can confidently rule out or prove the existence of this particle. And one of the few, or if not the only exception, is black hole superradiance. And the reason it is an exception here is because it doesn't require a coupling to the standard model. Instead, it's a purely gravitational effect. As I said, you just need a rotating black hole and need the mass to satisfy a certain condition. But once that is satisfied, you then have the superradiance process start, and potentially observable signatures emerge. And nowhere did you make an assumption about the coupling to the standard model. So it's purely a gravitational effect. And so therefore, even at zero coupling to the standard model, you might find observable signatures, which makes black hole superradiance such a powerful probe of particles beyond the standard model, because it doesn't require some coupling to the standard model. It purely requires gravitational coupling. Okay, and so then perhaps later down in the course, we might get to even more exotic things, perhaps. So for instance, once these clouds are formed and they have particular couplings to the standard model, we can then try and understand how does this behave. And so basically here, I'm looking at, so the central black dot is a black hole. And then you need to imagine that there is a superradiance cloud of massive vector bosons around it. And I'll get into the details of exactly what that means. But then if it couples to the standard model in a particular way, then you can see magnetic field lines emerge that kind of thread a plasma around the black hole. And then it turns out this is in a particular turbulent state, but it also emits a lot of X-rays. And so then on top of gravitational signatures, we can also look for EM signatures. So they can have a multi-messenger observation of these systems. And well, if you don't see anything, hopefully place constraints on the existence of these particles confidently. But then you can also have fun things like this. So again, here we're looking at a central Kerr black hole with a superradiance cloud around it. Again, it's a massive vector field, and again, I will get into what that exactly means. But now we are imagining that this mass is generated through a Higgs mechanism. And so basically what that means is that at low energies, so at low amplitudes of the field, the Higgs is basically just generating the mass, and the vector boson just behaves as if it just had a mass term. But as this amplitude grows and grows and grows, then the Higgs becomes important. And so eventually, what will actually happen is that the Higgs will no longer be in the symmetry broken phase, but it will be in the symmetry restored phase. And basically what happens then is that you form cosmic strings around the black hole. So here's a movie showing this. So you start out with just a black hole and a superradiance cloud, nothing around it. And then suddenly cosmic strings nucleate around the black hole. There's a very difficult to describe nonlinear process happening. And then the strings disappear, and then radiation goes out. Okay, this is just to say that there's a plethora of phenomena that are associated with this black hole superradiance process that build on top of just the gravitational coupling. Okay, so as I mentioned, the rough outline is the following. You start out with a Kerr black hole that has some particular mass and some particular spin. And so hopefully today, I'll briefly summarize the Kerr spacetime and kind of outline the most important bits that you need to know about Kerr. These include frame-driving things, but also black hole thermodynamics, which will be very useful in understanding energy extraction, and ultimately the Penrose process, which is basically kind of a particle version of black hole superradiance. Okay. And then, as I said, you have this cloud growing over some time scale because it grows exponentially and it is this bound state. And so then you end up with this cloud sitting around the Kerr black hole. And so basically, on day 2 and 3, I hope to cover the following. So we'll be focusing mainly on scalar fields, so Klein-Gordon theory. But I'll be mentioning a few things about vectors. It's basically analogous. It's just more algebra, and it's not very insightful. We'll do this in a test field approximation, and then we have to solve a bunch of PDEs. And there are very neat ways to solve these PDEs, so I think it's instructive to actually look at exactly how to do this. And then you end up with these equations for a quote-unquote gravitational atom, which are basically the hydrogen atom. And then we can start looking at superradiance instability more concretely, what it means and what the timescales are and how it actually pops out of the math. We can look at energy extraction, and then actually what happens, I was only telling you that there's a growth, an exponential growth, but what is at the end of this growth? Does it just keep growing exponentially forever, or does it stop at some point? And of course, it stops at some point because GR is a nonlinear theory, so there are nonlinearities in the theory inherently. And so as soon as this instability, this energy becomes too large, GR kicks in and regulates the instability. So we'll look at that too. And then I was mentioning, okay, we have continuous waves that are being sent out from these clouds. And to actually understand these continuous waves is quite involved and quite tricky. So I hope to present, at least in some shape or form, the linear metric perturbations, which basically are the gravitational waves that are being sent out. So this basically boils down to the source-Tolkowski equation. Again, I'll get into the details later down the line. And then we'll look at some way to solve these equations to get the gravitational radiation. And then lastly, of course, it's important, okay, now we have done all this heavy algebra and we have gotten some results, but now it's interesting, okay, what can we actually do with these results? Can we make observations that can either confirm these particles exist or rule out that they don't exist? And so that's basically covered on the very last day. So there we're going to look at exactly how to interpret the calculations we have done. We're going to look at how we can actually do continuous wave searches using ground-based or space-based gravitational wave detectors. And then we're going to look at some current constraints that have been placed based on these searches, and potentially look at the kind of the cutting edge, what's currently being done in this field. Okay, so let's get started. Now, the central object of interest is, of course, a rotating black hole. And a rotating black hole is described by the Kerr metric. And the Kerr metric is so central to this problem that I'll write it in the center and then hopefully add the stuff on the left and right so that you can always see the metric in front of you. Okay, so let me just write out the metric and then we can discuss what's going on. Okay. So this is the Kerr metric for those of you that haven't seen it. Basically, for A to 0, this reduces to just the Schwarzschild metric. And so A is basically called the Kerr parameter, where the angular momentum, let me make a little list here, where the angular momentum J of the spacetime is basically A times M. Secondly, it's asymptotically flat. So basically, if you go from R to infinity, then this entire, I forgot to define a couple things. If you go send R to infinity, then this will just be, the flat metric basically in spherical coordinates. Sorry? Yeah, I'll try my best. Okay. Then it obviously the metric itself doesn't depend on time t and azimuthal coordinate phi. So basically, you have a time-like killing vector, t mu, which basically generates the times translation invariance. And I'll try to write this bigger. So t mu is basically just the killing vector that generates the independence of this of time. And then analogously, you have phi, which basically just the killing vector that generates the azimuthal symmetry. Now, because of these, of course, for geodesics, you then have conserved quantities. So let me just define this because we'll need it later. P alpha, T alpha, and then the angular momentum is P alpha, phi alpha. So, right, Greek letters for me are space-time indices. Latin letters are just spatial ones. Right, and lastly, and this is kind of self-explanatory, we are restricted to the sub-extremal Kerr family. Basically, we're not interested in any of the mathematics that has to do with A greater than M. Okay. Right, and then the last thing I want to write down is that there are basically two horizons, but really one that is very important. So this is at so basically R plus is the outer horizon, R minus is the inner horizon. Mostly we're going to be interested in R plus because everything that happens inside we don't really care about here. Okay, and kind of implicitly I've already used a certain set of units. So let me write it here. Units. So basically I've set G and C to 1 in everything that wasn't the metric. And in fact, I'll do this throughout the remainder of the course because it's just a lot easier, less to write. And reintroducing the G's and C's is usually straightforward. So for instance, for mass, if I were to, for instance here, if I have a mass, then the way to reintroduce the G and C is basically just the mass goes to GM over C squared. But basically you can work out the units for anything you're looking at and then reintroduce the G's and the C's the way you need it to. Okay, cool. Now let's try and understand this metric. Because at first glance, it's not very intuitive and it doesn't really tell you much. Like by looking at this, you can't really tell what the spacetime is all about, what the differences are between this and Schwarzschild spacetime that you might be more familiar with. So let me list a couple of properties that ultimately will be quite important. Okay. So the first thing we want to focus on are 0, zero angular momentum observers, or ZAMOS for short. So these are basically observers that have vanishing L. So basically they're defined by L equals 0, where L is the angular momentum of some observer traveling through the spacetime. Okay, so what does this imply? What does L equals 0 imply? Well, L, as I wrote there, is basically proportional to U alpha phi alpha, where the momentum P is basically M times U. And what is U? U is basically, okay, basically you introduce some way of parameterizing your geodesic. And then let me just write this as a dot. We don't really care what the parameterization is. And then you have the spatial components. Right. So basically writing this out gives you the following. So what do we learn from this? By just rearranging things a little bit, we can then find that the following is true. So the change of the azimuthal coordinate of this observer with the coordinate time t, basically measured by an observer very, very far away, is the following expression. So this is just basically a bit of algebra where the metric components you can read off from the line element, and then you just plug it in. Right bigger. Yes. No. In fact, it doesn't really matter because here we're taking the ratio, and so the parameterization, this is independent of the parameterization. Okay, so now this is a bit of a convoluted formula. So one way of understanding this is, or to extract the most important physics is basically to take the r to infinity limit of this. And basically not the r to infinity limit, but basically the first non-zero term appearing in a 1 over r expansion of this. So the first term will look like this. And so basically what we learn from this is that even though this observer has no angular momentum, because that's how we constructed this observer to be, due to the angular momentum of the spacetime, so J, it will develop a non-zero angular velocity with respect to an asymptotic observer over time. And so, in fact, the closer it gets to the central object, the more important this effect will be. So basically, what happens is this is one of the frame driving effects that basically, even though the observer has no angular momentum, it then starts sort of moving with the rotation of the black hole. So it starts co-rotating with the black hole. Okay. Let me label this one. Static observers. So this was one way to understand, how the role, get some intuition for the role of angular momentum in this spacetime, but also in more general spacetimes that have non-zero angular momentum. Now, what about static observers? So static observers are those observers whose time, like the tangent to the trajectory, is basically proportional to the time-like killing field, T mu. Okay. And so let's look at the norm of this time-like killing field. Okay. So the norm is basically T mu, T mu. And so this is basically just a TT component, which is then this. Okay. And so this vector t makes sense as an observer only when t is time-like, right? Because otherwise it's not an observer that can travel anywhere. But as it turns out, this quantity, the TT component of the metric, is not necessarily negative. Yeah. Implicitly, I was defining the signature as minus plus plus plus, just to. So time-like vectors have a norm that's negative. So this is not negative definite. And so there are regions in the spacetime where static observers cannot exist, basically because the norm of this becomes positive. And so the region in which this happens is called the Ergoregion. And the Ergoregion is basically defined by the surface where t squared becomes null. So it basically changes from being timelike to spacelike. So where is this true? Well, basically it's true at sigma minus 2m r equals 0. And if you solve this, then we only care about the stuff that happens outside the horizon, so it happens to be the following expression. Okay, so how can we picture this intuitively? So imagine you have the horizon. So the horizon is just defined by r plus, which I was defining here. So it's a function of spin, but basically it's just some particular radius at which the horizon sits. But then as you can see, the region where this t squared becomes null does actually depend on the coordinates. It's not just the radius, but it depends on the polar angle. And so basically the way, and this is of course very gauge dependent, well, dependent on the coordinate system that you pick, but the way this kind of looks like is the following. So you have this region outside the event horizon that has some finite extent. That's called the Ergoregion. So basically what this equation means is that no static observer can exist inside this Ergoregion basically because T becomes space-like. Okay, so now we know what an Ergoregion, roughly speaking, is. So which observers can exist in the Ergoregion and are potentially of interest to us? Okay, so let's define the following observer, 3, orbiting. So we define the timelike vector, the tangent to the trajectory, to be proportional to t mu plus omega times phi. So this omega is basically just telling you, okay, we have some fixed angular frequency with which this observer kind of orbits around the central black hole. And then t, of course, to make it timelike. Okay. Now what we need to impose is that, okay, of course, the square of this u has to be smaller than 0 because it has to be an observer. We want it to be timelike. So what does this? What condition does this impose on the omega? Now I want to spare you the algebra because it's not very insightful and just give you the final result. Basically, omega has to be bounded by the following.
Years it can take place now in university, and this whole problems from the necessity.
Okay. So this is a bit of a messy expression, and this will kind of become a common theme, that there will be messy expressions, and we try to make sense of messy expressions. So let's plot this, and let's plot this for a particular case that is basically marginally extremal. And by marginally extremal, I mean A is basically M, but A is basically M, but slightly smaller. So, 1 minus epsilon, let's say. Okay? So for this case, we can plot omega. Oh no, let's not do that. We plot omega in the equatorial plane. So the equatorial plane is defined basically by theta equals pi over 2, just to get some intuition, as a function of r. Okay? And so at large distances, you have some asymptotic behavior for omega plus and for omega minus. And this asymptotic behavior should make sense, because of course, your linear speed is bounded by c, and so your angular speed around the center of the black hole cannot be infinitely large. Yes? Capital A. Pardon. No, this is a delta. Sorry. Okay, so we have this regime in which omega can sit. So basically, omega can sit in this regime bounded by omega plus and omega minus. But now the interesting stuff that is happening at the horizon, or towards the horizon. Okay, so let's say this is r equals m, the origin. And then this is r equals 2m, okay? So basically, if A is approximately not quite equal to m, then r plus is exactly m. And so, or exactly, approximately m, sorry. And so it kind of roughly sits at the origin here. And the ergo surface in the equatorial plane, that is theta at pi over 2, sits at roughly 2m. Okay, so basically we have the horizon here, and then we have the ergo surface here. And so what happens is the following. So this, the omega plus line asymptotes to some finite value on the horizon. And the omega minus line, we already know that on the surface, an observer with omega equals 0 can marginally exist, right? So basically, the omega minus must go through 0 on the ergo surface. Okay, so it does something like this. And then as it turns out, this is proportional to delta. And delta, defined here, is exactly 0 on the horizon. And so the reason for this is because you can factorize it in this particular way. And so this is 0 on the horizon, and therefore the second term vanishes. And so both r plus and r minus need to take the same value on the horizon. So they kind of meet somewhere there. So what have we learned? Well, we have learned that inside the Ergoregion we can have time-lag observers that exist, but there's some condition on these time-lag observers and how they can orbit the black hole. But more importantly, or perhaps more interestingly, they converge, or the condition on the angular velocity converges on the horizon. And it converges to what's called the horizon frequency, omega h, which is a over 2m r plus. Okay? So on the horizon, r plus and r minus take on this value. Now, why is this called the horizon frequency? Basically, of course, the horizon is not really a surface on which you can stand, but in analogy to some planet or some star, the idea is the following. So you have let's take the Earth, okay? And then we're standing on the Earth, And we are rotating around the center while standing there. So we have some fixed omega. And this fixed omega, as long as we're not moving, is the same omega as the Earth. And so we are assigning this omega that the observer is just sitting there to the angular velocity of the Earth, or it's the same thing. And so now we're kind of doing this leap in which we're saying that this omega h, so basically the angular velocity of an observer at the horizon is quote unquote the horizon frequency, the horizon angular velocity. So just to give you some intuition for what this omega h is, this will be very important for most of the rest of the course. Not so much the interpretation of what it is, but the omega h will pop up everywhere, basically. Okay. Now, okay, so far we've been talking about observers and try to understand intuitively that way what properties the Kerr spacetime has. So now let's try and understand, okay, what happens if we throw something into the black hole? So we're not just outside, but we throw something in. Okay, so for that we need to define a couple of things and build up a bit of machinery that will be useful in the next couple of days. So let's define what the horizon area is. So this is not necessarily a very straightforward thing to define because the horizon itself is a three-dimensional null surface. So what do we mean by area? So let us consult a conformal diagram. Is everyone familiar with conformal diagrams? There's some amount of nodding, but not universal nodding. Okay. Okay, let me give you like a 2-minute primer on what conformal diagrams are, and if it's still confusing, just come and talk to me afterwards. Okay, so let's look at Minkowski perhaps. So we have time, and then we have radius. So let's write Minkowski in spherical coordinates. And then from time and radius, let's switch to advanced and retarded times u and v, and I might confuse u and v. So far what we have done is, okay, we have just written it in spherical coordinates and then did some coordinate transformation to rewrite the t and r in terms of u and v. But now the idea is, okay, to get a handle on kind of quote unquote the causal structure of the spacetime, we can compactify coordinates u and v along the coordinates u and v. And so basically, all the space that's out there, you can kind of bring in to some finite u and v. And so the way this actually turns out to look like in the end is something like this. So basically here, these are R to infinity lines, so basically where, quote unquote, the space-time ends. Of course, it's asymptotically flat. And then the general intuition that, light travels on 45-degree angles here is still preserved. And that's kind of the key to understand these diagrams is that, if I send out a pulse of light here, it will travel like this and it will travel like this. Okay? Okay. I think that's right. And then perhaps one other thing is that, of course, if I draw a line like this, then this means I'm looking at a hypersurface that's space-like. And if I draw a line like this, then of course this is a hypersurface that's time-like. Okay? If there's still confusion, please talk to me afterwards. Okay. So now let's, oh, maybe I shouldn't erase this. Now let's put a black hole in the space-time and perhaps first look at what this looks like. Okay, so we have, of course, we know that, okay, Kerr is asymptotically flat. So at large R, we would expect the diagram to kind of look like this, right? Because here, again, the quote-unquote boundaries here are where R is infinity, and so this kind of should look like the same. as Kerr at infinity. Okay, so we basically have something like this, where again, these are lines where R goes to infinity. Okay, but horizons are also 45-degree lines. And the reason is kind of intuitive. So if you're a time-like observer and you're traveling like this, and you cross this boundary here, then you can never return to the original part of the space-time. So this is basically a horizon. Okay. So this corresponds to, in the Kerr space-time, this corresponds to the black hole horizon here. But of course, as you can see in the conformal diagram, it's a null surface. In fact, since I'm suppressing 2 dimensions here, any line is a 3-dimensional surface. So what's the area of this? In fact, if people talk of area most of the time, they're actually talking about the area of the intersection of this null hypersurface, let me call it H, and some Cauchy slice, let me call it sigma is not a good number, let me call it gamma. There's Cauchy slice, by Cauchy slice I just mean space-like hypersurface that slices space-time. So basically what they mean is that they mean the area of this intersection. I was just telling you that any line, so any 1-dimensional object in this conformal diagram is actually a 3-dimensional surface because it's suppressed 2 dimensions. So any point is a 2-dimensional surface. And in fact, this 2-dimensional surface here is a space-like surface. And then the word area makes a lot more sense for a 2-dimensional space-like surface because, well, the area of a sphere, the sphere is a space-like surface. Anyone can kind of have an intuitive understanding of that. Okay, so how do we find the area of this surface? Basically, we need to just read off some section of the metric. So ultimately, what we need to do to compute the area of the surface is to know, the metric in the surface. And the surface is basically just the theta and phi components, because it basically more or less happens at a constant t and a constant radius. Okay? So copying this here, I'm going to write the metric of this surface as the following. So this is basically just like the usual 4-dimensional space-time metric, just for this 2-dimensional hypersurface. Okay, and then just copying from there. Okay, so A and B just run, A is either theta or phi. Okay, and then the area of the surface is simply just the integral over the 2 coordinates of the determinant of this metric. And the determinant of the metric is literally just multiplying the 2 diagonal components and doing this, and then taking the integral over, d theta and d phi, you end up with 4 pi Now, if this was a bit quick, then this is actually part of your exercise for the tutorial today. So you'll go through the calculation more rigorously yourself, and you can see how these things work together. Okay, so now we have the horizon area A. And so how does the area help us understand, if I throw something into the black hole, what's going to happen? Well, Hawking showed in 1971, yes, that the area of a black hole the change of the area of a black hole, can only be positive or 0 under certain assumption of the matter that's falling in. But these assumptions are going to be satisfied for the remaining of the course. And so, okay, so we already have kind of an intuitive connection between you throw something in and the area seems to be important in some particular way. Okay. And so you can already kind of intuitively understand the area as something that is irreducible. And irreducible has a very precise definition in the context of black holes physics, and that is the irreducible mass that Christodoulou introduced. So the irreducible mass is basically related to the area by this formula. And of course, it's irreducible because you can't reduce the area under certain assumptions on the matter that you throw in. Okay. And then one last ingredient that we'll need. Well, there's 2 more ingredients, and both ingredients you're actually going to derive in the tutorial. So if this is all a bit quick, you'll go through this more carefully. Basically, for a non-rotating black hole, this area is, of course, basically just, well, the irreducible mass is basically just the mass of the black hole. This you can already kind of see intuitively from here. If you set A to 0, then there is an m squared left here. And so basically the irreducible mass is just the mass of the black hole. But now conversely, because the A is non-zero for Kerr, this is no longer the case. And so the black hole mass is no longer equal to the irreducible mass. So there's some amount of energy in the black hole that is not irreducible. Okay? Okay, so what is this? So the Christodoulou mass formula, basically the formula that Christodoulou came up with, can be basically directly derived from this, more or less. And it looks like this. Okay. So basically, as I was just saying, the black hole's mass is no longer just the irreducible mass, but there's some angular momentum component there. And so basically, you have some rotational energy inside the black hole that is not tied to the fact that you can't extract it. In fact, that will be kind of the core of the Superradiance process, that in fact you can extract this type of energy while satisfying this condition. Okay, and so lastly, I need to introduce how this actually happens. So how does, if I throw into the black hole some amount of mass and some amount of angular momentum, how does the area change given those bits of mass and angular momentum I threw in? And basically, this happens through the quote-unquote first law of thermodynamics, of black hole thermodynamics. I should stress that there's no thermodynamic process happening. It's just a classical calculation that happens to look like a thermodynamic relation. In fact, you are going to derive this basically based on what's written on the board, and I haven't written down any thermodynamics. But nonetheless, it's typically called the first law of black hole thermodynamics. Okay, so what is it? So the change in area is related to the change in mass and the change in angular momentum in this particular form. Okay, so delta m is just a change in mass, basically the bit of mass that I throw in. Delta j is just the bit of angular momentum I throw in. Then the omega h is the horizon frequency that we defined somewhere over there. And this kappa is the surface gravity, which is for the purposes of this just a function of mass and spin. I hope you can still read this. Okay, so at the moment, this is just kind of like, okay, I'm just throwing formulas at you. But they're going to be important probably tomorrow. And you can also deduce something fundamental from this in the context of the Penrose process. So for those of you that are already familiar with the Penrose process, I just want to get everyone back up to speed. And so this will be just repetition for you. But I think it's essential to go through this step by step to get some intuition for what will happen down the line when we talk about waves instead of just individual particles. Because most of the intuition that you can get from the particles applies for the waves as well, just that it's a lot more hidden and a lot less intuitive to understand. Okay, so the first thing you need to know about the Ergoregion, or the thing you already know about the Ergoregion, is that inside the Ergoregion, T mu, so the time-like Killing, or the asymptotically time-like Killing field, becomes space-like. And so if you define the energy of some observer through T, then you might wonder, okay, does something funny happen if this T actually turns space-like inside the Ergoregion? And yes, it does. And so basically what can happen is that this can be negative for R smaller than RE. Okay, so negative here really kind of means if you could have a measurement, or if you could make a measurement as an asymptotic observer of the energy of this particle, then you measure a negative energy. But of course, if I were to be an observer inside the Ergoregion that measures a particle that has asymptotically a negative energy, I would still measure a positive energy because it's a local frame. But asymptotically, so with respect to T, it's negative. And so what this means is the following. If let me make a small drawing, basically just copying what's there on the board already. Okay, so we have the black hole, we have the Ergoregion. If I throw in particle 1, so particle 1, and of course particle 1, it emerges from infinity, it must have positive energy, because there's no negative energy particle at infinity, it can only exist inside the Ergoregion. Okay, so then here inside the Ergoregion, I come up with a convoluted method of breaking up this particle into two particles. Okay, particle 3, leaves the Ergoregion and happily goes out to infinity again. And particle 2 falls into the black hole. Okay, and we engineer this breakup process in such a way that the energy of particle 2 with respect to T is negative. Now we can't do that because, of course, we are breaking it up only inside the Ergoregion. And so E2 we engineered to be negative. Okay. And so then, of course, we know that E1 equals E2 plus E3. Or equivalently, the energy of the particle that goes out is E1 minus E2, but E2 is negative, so E1 minus plus the absolute value of E2. And so as long as E2 is strictly negative, so not 0, this is larger than E1. Okay? So basically, we have thrown in a particle with some energy E1, and then make it break up in a particular way, and then in return we got a particle P3 that has some energy E3 larger than E1. So we have gained energy through this process. So now the question is, okay, we have this convoluted way of breaking things up, and we got a particle back. But where did the energy actually come from? And of course, it comes from the black hole, but let's see how that actually pops out of the math. Okay, so let's look at the trajectory of particle 2. And let's, of course, we have, E2 is P2 minus P2 T alpha, and then L2 is P2 phi alpha. And then let's define C alpha, which is T alpha plus omega H phi alpha. Now, what is this Xi? This Xi is designed in such a way that it is null on the horizon. And the way to show that is just basically computing the square and then seeing that it is null on the horizon. But it also means that it is time-like just outside the horizon. Okay? So if we compute the following, then what we'll get? We'll get E2 minus omega H L2. But we know that Xi is time-like outside the horizon, and so there, this must be positive. Basically because there's a minus here, and then P is time-like. And so if we just do some rearrangement here, we can see that L2 is smaller than E2 over omega H. And so basically because E2 is negative, L2 is negative 2. Of course, omega H doesn't have to be positive, but we fix the rotation to be, if we pick A to be positive, which you can always do without loss of generality because you can just do a flip of the axes, then this is positive, and so L2 is negative. And so what we learned from this is that, okay, we observe the black hole absorbs this particle, And so it reduces the angular momentum. Because it absorbs a particle that has a negative angular momentum. By angular momentum conservation, the angular momentum of the black hole must reduce as it absorbs particle 2. And so in that sense, the Penrose process, by which we can extract rotational energy from the black hole, is self-regulating, because the more you do it, the more the black hole will lose angular momentum. And because this process depends on the presence of the Ergoregion, and the Ergoregion is defined by this formula, if A goes to 0, the Ergoregion disappears. And so basically, as you spin down the black hole, the Ergoregion disappears, and therefore at the end of this process, you can't extract more rotational energy. And so in that sense, it's self-regulating, because it removes the way to extract the rotational energy. Okay. So let's see. Okay. So now, this is one particular way of extracting rotational energy from a black hole. But then there are many other ways to extract rotational energy from a black hole. One of which is the black hole superradiance process. And that's basically the core of this course. So let me write it down. Black hole superradiance. And to get there, let me define a couple of things. And then after making these definitions, call it a day before going into the nitty-gritty of how to proceed. Okay, so as I was already telling you initially, we're interested in a scalar boson or a vector boson of some kind that can trigger this process. But now the question is, okay, what are the equations that we need to solve to understand this? And basically, none of the equations are on the board at the moment, because everything we've been talking about was just individual classical particles that fall into the black hole and then do something to the black hole. But now we're interested in these bosons with very, very small masses, okay? And so ultimately, they're described by a wave equation as opposed to classical particles. And so the theory that we're interested in, is everyone familiar with Lagrangian densities for field theories? Some nodding. There's a question? No? Okay. Okay, so I'm going to define this in an action. And if you're confused with what I'm putting on the board, please do talk to me. Okay, so we're interested in a particular theory in which this happens. And so basically, what we're interested in is the following. Where this is the action. This is the determinant of the metric. R is just the Ricci scalar. Phi is a real scalar field. These are just partial derivatives. And then, yeah, I'm usually a bit sloppy about this, but maybe I should be not so sloppy about this. So mu, exclusively mu, is going to mean this mu, which is the mass parameter of the scalar fields. So mu is basically the mass of the particular boson. And then here I'm going to temporarily introduce a C and an H bar, just so you can get the right numbers. So M here is the boson mass, and so we were usually working with this mu, which is not a spacetime index, which is the mass parameter of the scalar field. Now, I could have written down the Lagrangian for massive vector fields, and most of what I'm going to describe over the next couple of days will carry through exactly the same way. It's just that there you have a bunch of indices everywhere, and the algebra becomes more complicated. So we're going to focus on a massive scalar field instead, where we can do things analytically and in a reasonable amount of time. Okay. Right, so let's write down the equations that we get from this action. Of course, it's first the Einstein equations. So here we have where T mu nu is basically just the matter that is the scalar field. So the scalar field, the T mu nu you can derive from this is and as you can see, I was sloppy again, putting the mu's everywhere. So this is a lambda. Sorry. Okay, so this you can just derive readily from the action. And then equivalently, the scalar field follows the Klein-Gordon equation, which is where this differential operator is just the covariant derivative of, or just the covariant derivative. Okay. Okay, so now the general approach to these two equations, so basically the Einstein equation and the Klein-Gordon equation, is going to be perturbative. Because of course, in general, these equations are very, very difficult to solve, and so you can't really make a lot of progress analytically. But you can make some progress perturbatively, and ultimately what we're interested in is a Kerr black hole with something outside, okay? So there's already hints to you that this something might be described perturbatively, whereas the Kerr black hole is just a Kerr black hole, okay? And so to do this explicitly, let's write down the perturbation of the Kerr spacetime. Okay, so let's write our metric G alpha beta as G alpha beta Kerr, where the Kerr metric is what's written in the middle, plus some perturbation H mu nu, H alpha beta. And the way we're going to keep track of the orders of perturbation is just by some order parameter epsilon. So epsilon is just assumed to be small, some dimensionless number, to keep track of the orders. And then equivalently for the scalar field, the zeroth order is 0, because of course we need a nonlinear solution to the equations I wrote down over there. And well, Kerr spacetime is a vacuum solution, so T mu nu has to be 0. And then of course if phi is 0, then the Klein-Gordon equation is trivially satisfied. And so the zeroth order gives us a nonlinear solution to the set of equations I wrote down over there. And so then at first order, okay, it's just some scalar field phi, capital phi here, plus second order things. Okay, so now the general approach would be, okay, let's take this perturbative expansion and let's plug it into the equations over there. And let's try and understand, well, basically do a bunch of algebra to find the evolution equations for this capital phi and for the H alpha beta. For, I guess, the trivial case is the Klein-Gordon equation. So for the Klein-Gordon equation, you just get the Klein-Gordon equation back. Basically, you just get box minus mu squared on phi equals 0. So this is basically epsilon equal epsilon to the 1. But the Einstein equations are not so simple, because now you have a non-trivial zeroth order, and so now I shouldn't have written this on two different ends of the board. Now you have to plug this into the Ricci tensor, and then expand the Ricci tensor, which is some nonlinear function of G alpha beta. You then need to expand this Ricci tensor in terms of H to linear order, to then get some differential operator on H that gives you the equation. I'm not going to go through that algebra, because I think it's really just algebra. But the final result I'm going to quote, and it's also not going to be very important for the rest of the course, but it's an equation that pops up every once in a while, so it's kind of good to have seen. So the perturbative equation for H alpha beta is the following. Gamma delta. Under the assumption that, and this is kind of a gauged choice, maybe I shouldn't. Okay, so these last two equations are basically just gauged choices you can make. Just kind of, let's say, coordinate choices you can make to set H into a quote-unquote Lorentz gauge and set the trace to 0. This you can do as long as there's that 0 on the right-hand side. Okay, and so basically this just gives you the evolution equation for the linear perturbations of the metric. But what you'll already see is that at leading order in epsilon, so these two equations are basically epsilon to the 1, right? At at linear order in epsilon, the metric isn't sourced by anything. So the metric is just freely evolving by itself and completely decoupled from the scalar field. And vice versa, the scalar field is just freely evolving and decoupled from the h mu nu. So now we have two decoupled equations. And in fact, you're really only interested in the first one, this one, because here, what this describes is a kind of gravitational perturbations on a Kerr background. And generally what will happen with those gravitational perturbations, they will decay first exponentially and then a bit slower in time. Okay, so maybe, let's say after a binary black hole merger, you have some perturbations around the remnant black hole, and these perturbations will, decay away over time. And this decay is described exactly by this equation around the Kerr spacetime. And so we can kind of just assume, okay, no, maybe these perturbations have just decayed away sufficiently for us to say, okay, h alpha beta equals 0 is a good approximation of our system. Because ultimately we're interested in isolated black holes that have existed for a while, that haven't merged in the last, however many milliseconds. And so this is a good approximation to try and understand what we're interested in. And then here, you might naively say, oh, okay, phi equals 0 is also a solution. And that is true. However, small perturbations of phi will lead to this exponential growth that I was talking about. So what this means is that the solution that is phi equals 0 is unstable. And so in some sense, phi equals 0 is not a good solution because the system, if you just poke at just the smallest amount, will move away from that solution exponentially quickly. Okay? And exactly how it moves away from that will be, again, discussed over the next couple of days. But that also means that phi equals 0 is not a good solution. Instead, we need to look at non-trivial solutions of phi to this Klein-Gordon equation. And that we'll do tomorrow. Any questions? Yeah, there will be a condition. Yeah, I can't write on the condition because we haven't defined enough machinery yet, but there will be a condition on when this happens. Yeah. From this equation? Okay, so basically because we engineered the process of breakup of this particle 3 in such a way that the energy of particle 2 is negative. And so then this is basically this is basically telling you that L2 is negative. And so now I'm throwing this particle into the black hole that has negative angular momentum. And so basically what that means is by angular momentum conservation, the black hole will reduce angular momentum. For non-trivial?
H alpha beta. Like when the metric perturbation is non-trivial, and you take perturbations in phi, then only it is unstable?
No, it is unstable if this is satisfied. Yeah. In fact, it will also be unstable if this is not satisfied because the two equations are decoupled. So even if H is some non-trivial solution, because this equation decouples, and it is unstable for H equals 0, this will also be unstable for H not equal 0. Yeah, just the Kerr black hole. So the metric is literally just the Kerr metric, up to quadratic effects in epsilon.
And you're saying
And in fact, we'll show that tomorrow or the day after tomorrow, that that's the case. Okay, what is the exotic black hole space then? Right, so, right, I don't want to make a general statement that any black hole, because I don't know. But I would imagine so. Like, for instance, for a charged black hole, you have a similar expression that involves the charge as well. But there's kind of a general procedure to derive this, so I imagine in general it may be true, but I don't want to say that out loud. Right, right. Yeah, so so that is a dynamical context, and so the conformal diagram I drew was of Kerr, and Kerr is stationary, so it's non-dynamical. And so if you were to draw a dynamical version of this, it would look something like this, I believe. So you have the horizon at early times, and you have a horizon at late times, and then they kind of get connected. And so the area increases from here to there. Okay. All right, thanks.